Next presentation is from Rojen Malachi. He is a technical support director for Europe at GCL Silicon, and he's going to speak on fully vertically integrated value chain, GCL's commitment to reliable solar energy. Rojen, the floor is yours.
So, welcome everyone, and thank you for joining. My name is Rojen Malachi, and I'm the technical director for GCL SI in Europe, and I'm based out of Munich in Germany. Today, we're diving into a topic that ultimately defines the success of every solar asset, PV module reliability, and specifically how GCL designs, manufactures, and validates modules for long-term performance and predictable energy yield. Our objective for today is to show you how GCL's technology, materials, and manufacturing philosophy deliver durable, stable, low degradation PV modules. Over the course of the next 20 minutes, I will be talking about the following topics. This includes GCL's vertical integration, our low carbon FBR granular silicon, product reliability improvements, back contact, or as we call it, GPC reliability features, a bit about the next generation TOPCon 2.0 and 3.0 updates, and also finally the future potential with perovskite technology and focus on single junction and tandem. A bit about the group. So GCL is one of the most established solar technology groups globally with more than 30 years in the energy industry. We have a vertically integrated platform from polysilicon to ingots to wafers, cell, and modules, supported by over 3,000 patents and multiple gigawatt scale manufacturing bases across China. This long-term industrial base allows us to optimize reliability at materials level, process, and the product level, something only a handful of players in the industry could do so far. PV module makes up only a part of the group. We are also an independent power producer, or IPP, as well. A key competitive advantage for GCL is its vertical integration, meaning we control critical material and process steps ourselves instead of relying on third-party supply. For material reliability, that matters because material purity starts at the silicon atom level, wafer micro defects determine long-term behavior, cell passivation determines early life and long-term degradation. By controlling each step, we ensure the mechanical stability, electrical and stable degradation curves, and ultimately predictable system performance. This slide illustrates GCL's vertically integrated value chain, starting from the metallurgical silicon in Inner Mongolia. We move to FBR granular silicon, then produce the ingots. From there, we manufacture wafers, cells, and finally modules in locations in Wuhu and Hefei in China. Here, we want to highlight why GCL stands out as one of the very few companies with fully vertically integrated value chain. We cover every stage from the metallurgical silicon extraction to polysilicon, ingots, wafers, and cells, and finally modules. Most competitors only integrate partially, either starting from the polysilicon or focusing on wafers and cells. In fact, among the top 10 PV module manufacturers, GCL is the only company that achieves full integration from raw material to finished module. This gives us unmatched control over quality, cost, and sustainability. At the foundation of our reliability story is our silicon. GCL pioneered FBR granular silicon at industrial scale, which offers reliability advantages versus traditional Siemens polysilicon methods. From a material science perspective, this translates to a more stable module over time, and as a bonus, significantly lower carbon footprint. Our FBR silicon is used 100% in GCL cells, and we ensure sustainability by recycling leftover materials within the production cycle. In addition, we maintain extremely high purity standards, allowing less than 0.5 ppb or parts per billion of impurities. This guarantees superior quality and performance for our cells. Here we want to show how FBR granular silicon significantly reduces emissions and resource consumption compared to improved Siemens method. You see the power consumption, water usage, hydrogen consumption, and labor costs are significantly down. Most importantly, the CO2 emissions are reduced by 75%, setting a new benchmark for clean manufacturing. The technology achieves a verified carbon footprint of just 14.4 kilogram carbon equivalent per kilo of product. This is the lowest recorded value in global polysilicon production, establishing a new industry standard for sustainability. Full traceability means every module can be traced back through the silicon batch, wafer, cell lot, production line, test data, and field deployment data. This supports reliability, analytics, and transparent warranty claims. We want to highlight that these are not just data that GCL maintains for supply chain mapping, but have been independently verified by an independent agency, TÜV Rheinland in this case. And these are the results of the audit from TÜV Rheinland regarding traceability. As you can see, it's around 80% with a AA rating and 20% with an A. So this highlights a level of transparency in GCL's supply chain. With these advanced traceability features, we're able to put this into our Cyro module line. Every Cyro module comes with a QR code that links to a website that provides 100% traceability. In addition, the data has been securely placed in the blockchain, so this is tamper-proof as well. Coming to the heart of today's discussion, I will be talking about GCL's endeavors towards improving reliability. Early life degradation impacts investor confidence and first-year yield as well. In this slide, I want to focus on UVID. In the graph, you can see data from the beginning of the year from GCL Labs, where we compared certain competitors who had issues with UVID 60. So all the results are UVID 60 with up to 5% degradation. Our enhanced passivation stack and process control limit UVID to around 1.2% for exposure of UVID 60 with controlled recovery behavior. On the bottom side, you can also see the differences in EL images for GCL's UV resistant cells compared to conventional cells after UV exposure. Talking about powered STC tests, we have heard of cases in the market where flashed power is below the actual power and sometimes even by a couple of percentages. And that, when you look at the percentage-wise, that's really a lot. GCL comes through a significant flasher calibration process. We maintain precise output calibration through round-robin referenced golden samples, tightly controlled flash test calibration, and also the power control bin. This reduces mismatch losses in projects and ensures delivered wattage meets or exceeds nameplate. So basically, you get what you paid for and not just theoretical numbers. Back glass durability has been a major industry topic, and we've heard of some manufacturers with modules that have lots of issues on the rear side of the glass. This could be because of the mesh coating that's used. To overcome this, GCL uses a redirecting film to improve the tempering of the glass. This minimizes spontaneous glass fracture risk, and this, at the end of the day, is a lot to do with the thickness of the glass and how the thickness has been reducing over the last years now. So reliability is not just electrical, but also on the mechanical side. So for GCL's NT12R66 GDF, or the golden reference bifacial dual glass modules, we see the standard IEC 61215 aging test results here. So this includes the damp heat or DH1000, the TC200, and also UV15 results. So the degradation is much lower than the IEC requirements of 5%. We go beyond the minimum requirements of the IEC and even do 3 times the IEC 61215. So this goes to the damp heat 3000, TC 600, thermal cycling 600, UV 60, wet leakage current test, LETID, salt mist 8, PID. So all of these extended reliability tests, also the results are far below 5%. So some of them are 1.5%, 0.2% in some cases. So all of this with this, we're able to give a high confidence for the decades-long warranty that we give as part of our warranty. Here we show the percentage of cumulative power degradation over 3 years. So we have a first-year warranty of 1% and a yearly degradation of 0.4% after that. So in this case, you can see our first year is 0.86% in this case. The second year is 1.37%, and the third year is 1.63%. All of this is far below what we guarantee. So with this, we want to show that our modules can consistently deliver annual degradation below those guaranteed in GCL's limited warranty statement, and therefore supporting long-term yield predictability. Now coming to the back contact modules, or as we call it, GPC, let's focus on some of the core innovations that deliver superior reliability for our back contact or GPC 2.0 modules. First, we utilize low temperature soldering. This is critical for overlap designs because it drastically reduces the internal thermal stress. The result is a simple but massive reliability gain. Microcracks are reduced to almost zero. Next, we optimize the manufacturing flow by using half-cut wafers from the start. Processing wafers in this format improves efficiency and consistency. This precision directly translates to performance, improving the power bin by one class on a module level. Third, our design offers advanced hotspot protection by utilizing the PN junction on the cell level. Shading does not cut off the entire cell string like in some conventional designs. Crucially, the current flow is not fully restricted for back contact cell, giving it superior performance and reliability compared to technologies like TOPCon under partial shading. Here again, just to focus on the reliability features of GPC 2.0, here specifically the shading. So conventional modules trigger the bypass diodes once roughly 10% of the cell string is shaded, which results in lost power and local heating. With our GPC design, optimized cell patterning and circuit layout, this increases the activation threshold to around 20%. This means that module continues generating efficiency even under partial shading conditions, delivering high real-world energy yield. Another reliability benefit is hotspot suppression. In conventional architectures, shading forces current through blocked cell areas, causing local overheating and accelerated aging, and in extreme cases, even fire risk. Our reverse current operating control technology avoids this by letting current bypass the shaded zone smoothly, preventing thermal spikes and protecting the cell architecture. Finally, GPC modules minimize microcrack formation and spread. Traditional modules often use a Z-shaped busbars, which create stress concentration points. This means cracks can propagate, eventually leading to hotspots and power loss. Our design uses linear busbars with even stress distribution, dramatically reducing crack initiation points and ensuring stable output even if microcracks occur. In short, back contact architecture improves shade tolerance and mechanical resilience, both critical for long-term reliability. Taken together, these design choices translate into higher real-world performance, lower degradation risk, and greater assurance for asset owners, especially for back contact in rooftop environments where shading and mechanical stress are a concern. Next, moving on to our next generation TOPCon 2.0 and 3.0 module platforms, we want to focus here on the cell size and stress management. For these TOPCon 2.0 and 3.0 platforms, we use smaller cells, typically 3-cut or 4-cut formats, instead of the large full cells or even half-cut. This has two important reliability benefits. First is the temperature operating current at the lower operating current, which significantly improves hotspot resistance. Low current means that if a portion of the module is shaded or stressed, local heating is minimized and hotspot formation is much less likely. Second, smaller cells greatly reduce the risk of microcracks and slow crack propagation. Large format cells are mechanically more fragile and cracks can spread faster across a large silicon area. By reducing the cell size, we distribute mechanical load more evenly and increase module resilience to transport stress, installation stress, wind load, and thermal expansion. So overall, smaller cell TOPCon architecture gives us stronger thermal stability, better mechanical durability, and enhanced long-term performance, especially in real-world conditions where modules face vibration, thermal cycling, and uneven mechanical loads. This slide highlights the reliability improvements achieved in our TOPCon 2.0 and 3.0 using 26 bus bars compared to the traditional or the newest generation of 20 bus bar designs. First, under identical conditions of microcracks and broken grid line, cells with more bus bars experience a smaller impact area. This means the 26 bus bar cells have a higher tolerance for microcracks and fractures, reducing performance losses during module operation. Second, after soldering, the stress distribution on the cells is more uniform. The force applied by the solder ribbons is spread evenly, which minimizes packaging stress and enhances the mechanical strength of the cells. Overall, these factors significantly improve module reliability, as illustrated in this figure, comparing microcrack impacts on cells with different bus bar counts. Here, I want to drive home the reasons as to why crystalline silicon alone cannot meet future efficiency targets and why perovskite and tandem technologies are essential. Crystalline solar cells have been the backbone of the industry for decades, but they are approaching their theoretical efficiency limit of around 29%. Even with advanced designs, we cannot go beyond this barrier because of the fundamental material constraints. Perovskite cells, on the other hand, have shown rapid progress, reaching efficiencies close to 26% in just 10 years compared to 50 years for silicon. However, single junction perovskite cells also have a theoretical limit of around 33%. The real breakthrough comes with perovskite silicon tandem cells, which combine the strengths of both the materials. By stacking two complementary absorbers, we can capture a broader spectrum of sunlight and pushing efficiencies up to 45%, far beyond what silicon alone can achieve. This is why tandem technology is considered the only viable path to significantly higher efficiency and lower cost per watt in the future. This slide highlights a major milestone in reliability for perovskite technology. In May of last year, our 2 square meter perovskite single junction module became the first in the industry to receive third-party certification from TÜV Rheinland under the IEC 61215 and 61730 standards. In addition, the module successfully passed 3 times a reliability test based on IEC 61215, including damp heat and thermal cycling. These tests validate the durability and long-term performance of module under real-world conditions. Note that because of the tandem architectures that introduce new materials and interfaces, there is currently no dedicated IEC 61215 standards for tandem perovskite technology. However, the industry is actively working to adapt these standards, and our certification sets a strong precedent for future developments. So just to also show you that the GCL has its first gigawatt scale tandem perovskite production line. The first commercial modules rolled out of this factory a few weeks ago, and this demonstrates our commitment to turning advanced research into industrial reality and investing significantly in commercialization of the next generation PV technology. So to conclude, material reliability starts at the silicon level. Vertical integrations ensure stability and consistency. Stress testing exceeds industry norms, and real-world data confirms long-term durability. That's it from my side. Thank you very much.
Okay, thanks a lot, Rojen. I think that's great news that you have commercialized the perovskite module. So these are tandem modules, or these are just perovskite modules?
So the factory as such already had a single junction production line that's been running, but now the biggest news was the tandem modules that have started rolling out of the production line. So that is the big news from a couple of weeks ago.
And so is it initially available only in China, or where are you going to?
So the plan is that by middle of next year, this is to be launched globally, but at first it is going to be available in China. Yes.
Okay. So I have a few more questions, but I think I will reserve them for our panel later.
Yes.
When you are joining. So then let me move to the next presentation.
Okay. Thank you.
Yeah. Thank you.